Fine. So today we are going to talk about evaluation and benchmarking. This is something uh, which people least focus, right? But this is the major driving force for all sort of innovation that is happening these days. And I'll explain why people least focus on this thing, but again, why this is very important. Okay, so how many of you have seen what MMLU benchmark is? You are kind of 100% confident about like what MMLU. You have heard this name, right? MMLU several times in this school. But have you visited this particular benchmark? What exactly it is? Maybe just one of you. I can see just one or two hands being raised. Okay, we'll see what exactly it is, right? But why this slide is shown here is to just show you the progress that has happened in last 4 years, 4 years or 3.5 years for this particular benchmark, right? So we started with BERT type of models. Roberta was one of the most popular BERT-based model, right? And if you see the performance on MMLU benchmark, it was around 27, 28 that time in around Jan 20, right? And right now we are here, almost here. So again, so no one has passed Gemini ultra performance, but probably GPT-4o has done that. So those numbers are not here. Okay, so but if you see this performance, we are reaching almost 100%. 100% performance, 100% accuracy for this particular benchmark. Okay, we'll see what exactly is this benchmark, but just let us just see how the models are going. Okay, what will happen if suppose we reach 100%? What do you think will happen then? If suppose we reach 100, then we'll create a new benchmark. People have already created another version of MMLU, which is more difficult than this traditional MMLU, right? Do you think models which are doing that good here, they will do good always in all real scenarios, I should say, right? So I'll show you some examples where it has been proved that models which are doing that good on these kind of benchmarks are actually trained on these benchmarks. Okay, so some data leak has happened, and it can be proved that that data leak has been happened, so that the models are doing that good, very good on several set of benchmarks. Okay, even though the model, the creators of those models will say, no, that has not happened, but it has actually happened. It can be proved. Okay, so even though many of these models are reaching almost 100% accuracies for this particular benchmark, they might not be that accurate in real scenarios. Okay, we'll see examples. Okay, before kind of going to those nitty-gritties, let us just revisit our traditional NLP, the way we used to see NLP before this deep learning era came, right? So earlier, we used to have two major tasks in NLP. The first type of task, we used to call that as classification task. The other we used to call as generation. Okay. Regression again is a very important task in ML, but not very popular task in NLP. Fine. So within classification, we can have tasks like spam detection. We can have tasks like authorship detection. So you are given a piece of text, and then the model has to identify who is the author of that particular passage or a paragraph or a text, right? So that is authorship identification. Then age, gender identification. Maybe some tweet has been written, and the model has to predict what is the gender of the person which has kind of posted this tweet. Okay, or what is the age group of this person which has posted this tweet. So that kind of models are also there. Again, these are all classification models. Then language identification. So a piece of text is given to the model, and model has to predict that, yes, this is English with this much confidence, right? This is Hindi with this much confidence, or maybe this is mix of Hindi and English, Hindi this much percent, English this much percent. So those kind of models are also there. And then we have these very popular sentiment analysis models. Right, sentiment analysis, you know what is sentiment analysis. So again, these are classification type of models. Okay, so Hugging Face, all of you have visited so many times last kind of 7-8 days. Okay, so what is the most popular text classification task on Hugging Face? Try to find out the answer. the most popular text classification task on Hugging Face. Because classification you can also do in for vision task, right? So text classification task. It is actually sentiment analysis. Try to find out how many models are uploaded on Hugging Face for just sentiment analysis. People might think that, so no, this task has been solved, right? This is already solved task. Try to see the number of models that have been uploaded on a daily basis and in general for this Hugging Face, on Hugging Face for sentiment analysis. Maybe Himanshu, can you just find out and just tell me that number? It will be in thousands. It will be in thousands. We did some study. Again, we're not presenting here, but it is in thousands, right? Okay, we'll show you some nice results for the sentiment analysis models that are on Hugging Face maybe towards the end of this presentation. So why not just blindly use any sort of sentiment analysis model from Hugging Face? There are some issues there, right? We'll talk about that towards the end of this lecture. Okay, fine, but sentiment, you know that, right? Now suppose you are given three reviews. Okay, so the first review is this laptop is a great deal. Okay. The second review is a great deal of media attention surrounded the release of the new laptop. Again, both of these are laptop related sentiment. And the reviews, the third is the film should be brilliant. It sounds like a great plot. The actors are first grade and supporting cast is good as well. And Stallone is attempting to deliver a good performance. However, it can't hold up. So we have the same word, the positive, highly positive sentiment word great in all these three reviews, right? And do you think the sentiment for each of the three sentences are different? Even though the very highly positive word great is present in all these three. So what is the sentiment of the first one? Positive. The first sentiment, the sentiment of the first sentence is positive. The second one, this is neutral with respect to the laptop. This is neutral with respect to the laptop. Third one, it is negative with respect to the movie, right? It is negative with respect to the movie, right? And this is where all sort of challenges will prop up, right? That is why we have so many models uploaded on Hugging Face. Still, like still people are coming up with new models, trying to compare the models with the existing models, and then they say that no, our model is better than what has been proposed. Okay, but this is how the things are happening. Again, if you see it, this problem looks very simple. It is not that simple, right? We have not yet even talked about sarcasm. It is very simple, non-sarcastic sort of sentences. Again, detecting sentiment is difficult here. Okay. The other task is generation, of course, right? Generation in NLP is a popular task these days. And some examples could be summarization, the question answering, machine translation. Okay, again, there are many such tasks. I've just listed three here. So if I have a sentence in English, can you imagine saying that we are looking for this kind of a generation in Hindi? Okay, again, this is a generative task. We are generating new set of words, new set of sequence of tokens from the input tokens, input sequence of tokens. Okay, fine. This looks good. Nothing special. Okay, given these two types of categories of task, we also have two categories of evaluations. Okay, the first category is called close-ended evaluations. The second category is called open-ended evaluations. Okay, so the type of things that we were doing in case of classification. First one, you have limited number of potential answers or ground truth answers, right? So maybe in case of sentiment analysis, when you are going to train your model on that data, so you have a sentiment and then some annotators have added the label, whether the sentiment is positive, it is negative, neutral. And then there can be multiple annotators which are assigning some labels to the same sentence, right? And then I take the majority. Okay, so maybe for a given sentence that you have as a review, 5 annotators were picked. 3 of them said that this is a positive review, 2 said it is a negative. So what is the majority? Positive. So I'll say that no, this is a positive kind of a review, right? So in close-ended evaluations, the data that is available is going to be having limited number of potential answers. Okay, often one or just few correct answers, and it enables automatic evaluation as in machine learning, right? So most of the traditional ML that you have seen before this deep learning era, generation era came, all these all were open-ended evaluations. Right. You have fixed set of ground truth answers and you have to match the predicted answer with the ground truth answers. Okay, so in some way, we'll see what are the ways to do it, but in some or the other way. In case of open-ended evaluations, where this is used, so suppose we are going to generate text, right? So we have long generations with too many possible correct answers to emulate, right? So given a paragraph, I want the model to summarize it. Again, there can be different ways to summarize the same paragraph, right? So it is kind of an open-ended task. Even some you have employed some annotators who have created ground truth summaries, but that might not be sufficient. Model might come up with a new kind of summary, which is even better than what you see in the ground truth summaries. Okay, so those kind of evaluations are called open-ended evaluations. So earlier we just had right or wrong, but this time we can also have better or the worse answer. So something is better than what ground truth has provided, right? Or maybe one response is better than the other response. One response is poor than the other one, right? So those kind of things can happen. So these are open-ended evaluations. So let us talk about some open-ended or some closed-ended tasks. This is where we will revisit different websites, different papers, and we will see how exactly they look like, right? Most of you have heard these names, but what is important is to actually see them, how they look like, right? So within a closed-ended task, we have the first one, the most popular one, which is sentiment analysis, right? All of us know. And all of us know that SST is some sort of a some benchmark, right? What is the name of this benchmark? SST. Why what first S stands for? Sentiment. What is SST2? So what does 2 means? You have used it before, right? How many of you have used this model, this benchmark, this data set before? You have used SST, right? You have used SST2 or 5? 2. What does 2 stands for? No, right? That is why this class is important. Classes. Yes. The 2 or 5 represents classes. SST2 has just 2 classes, positive or negative. SST5 has 5 classes. We'll see what are those classes. Okay, so I'll just show you what exactly they are. Just give me some. Okay, so SST stands for Stanford Sentiment Tree Bank, which is kind of different than what you have thought about, that it's like given a sentence, it is going to have some labels, right? It is not that case. So the way this has been created is you are given a sentence. You have given the sentence to a human. First, you have given the sentence to a parser, and that parser creates this kind of a parse tree. The sentence is passed to a parser, and parser is again kind of a model, right, which creates this sort of a parse tree for the sentence. And then this parse tree is provided to the annotators to annotate different phrases, right? So if you see here, this particular phrase, this film, it is 0, or this is kind of a white, right? So this film is what label? Neutral. It is neutral. right? This is one phrase. Then this is doesn't. What is the root of doesn't? Negative, right? That phrase doesn't is a negative phrase. Care is positive. About is neutral. And then cleverness, wit, or any other kind of intelligent humor. So idea is that you are given a parse tree and different phrases in the parse tree are given some labels, right? And then based on this label, again, these are assigned by humans. These are again assigned by humans. So, and then based on this parse tree, so you assign labels to each of the parse tree, and then you also assign one label to the entire sentence. Okay, but that is how this SST dataset looks like if you have not seen it before. Okay, one more thing. So the corpus SST5 is going to have 5 labels. That's why SST5 is very popular. And what are the 5 labels? Negative, somewhat negative, neutral, somewhat positive, and positive. What is more popular is SST2. So in case of SST2, you are combining negative and somewhat negative classes together, somewhat positive and positive together, and then you are discarding neutral. So you're left with just 2 classes. Okay. And this was proposed by the team of Stanford researchers. That's why it is called Stanford Sentiment Tree Bank dataset. Okay. Again, if you see the number of papers that have used this dataset over the years, it is very popular. Almost minimum 200 papers are using SST dataset every year. Very popular dataset, but you should be careful. What is this data, and what are the classes? What does this different things means? Okay, one more question. People have used SST. What does it contains? It contains review from which domain? Reviews could be about products. Reviews could be about some restaurant, right? Reviews could be about some service. Movie. So this was on movie dataset. Right? This is on movie dataset. Okay, fine. So if your model is trained on this dataset, right, probably it might not work for a domain where you want to work it, where maybe you want to kind of use it, and that domain could be retail, suppose, right? So you have trained your model on this, and suppose you want to deploy this model on Amazon. Probably it will not work. Right? What people do is people just pick models from Hugging Face, trained models from Hugging Face. They will just see the name. Oh, this model has been trained on SST2. Let's just use it and deploy. Again, even though it was giving you kind of 98% performance on SST2's test set, it will not do good on your data set, on your kind of use case, right? So we need to see that. What models are trained on what data sets? Okay, SST2 is done. What about IMDb? IMDb, how many of you have used this data set? Many of you, right? And many of you know that this is again movie review data set. Okay, IMDb is a website, and the reviews are curated again by Stanford people, Stanford researchers, and this is the data set that we were talking about, right? This is large movie review data set. Okay, it was published in 2011. I think a newer version of IMDb data has also come, right? This is the version 1 of the data set. Okay, so there are around 50,000 reviews, 20,000, 25,000 for training, 20,000, 25,000 for test on this data set. Okay, fine. This is also very popular data set for sentiment analysis. Then we have the third one, Yelp. How many of you have used Yelp data set? Have you heard this name, Yelp? No? Okay. Okay. So who has used Yelp? So what is Yelp? It is a restaurant data set. So ratings about food, ratings about restaurant service, everything is available here. Again, a very popular sentiment analysis data set. Okay, so I'll just click here. I'll show you how it looks like, because clicking and seeing here is kind of very important. Okay, this is the Yelp open data set. Again, if you see the quality and the quantity, it is very good. This is one of the very well maintained data set, and from the parent organization itself. So Yelp itself maintains this data set very well, and they kind of update it also regularly. So the reviews are huge, almost 6 million, almost 7 million reviews, right? 7 million reviews are there. Almost 150 restaurants, 150,000 restaurants are reviewed, which are reviewed are there on this data set, right? And then it also has pictures, right? Pictures of different food that was served, surveys related to service, and about maybe the inside of the restaurant, the outside of the restaurant, all these things are there, right? And then pictures with some sort of captions, right? So it is not just you can use this data set for text analysis, you can also use it for building some image models. Okay, so that is also possible here. No, reviews, the for sentiment, you have this the review data. That is separate, right? But again, all this is available, publicly available. You can use it. Okay, just click on download data. It will tell you what exactly, and again, it will ask you to kind of enter a few things. But again, a lot of you can click on the documentation. It will tell you exactly what does the data look like. Yeah. So this is how the restaurant specific information look like. The reviews information look like. Great place to hang out. What are the useful votes received? What are the funny votes received? Cool votes received? Right. So all these votings are there in this data set. User related information is also there, again anonymized. Tip related, how much tip was given, all those information is also there, right? And then photo information is also there. There is a separate directory, it gives you kind of link to that directory, download the pictures there. So that is all possible from this Yelp data. Fine. So okay, these are different data sets, and then I'm just presenting one such example. The example sentence is read the book, forget the movie. So what is the label here? Is this the correct label? Read the book, forget the movie. Why the label is negative? This is negative with respect to what? Movie. The movie is not good, so maybe instead of watching movie, you can read the book. Okay, so again, we are not in detail talking about sentiment analysis, but again, this is very important. What aspect we are going to, with what aspect we are talking about, and kind of what property of that particular aspect we are also talking about. Okay, again, let's not talk about that. Okay, SNLI. SNLI is also a classification task. What is the SNLI task or dataset benchmark? S is Stanford. Okay, natural language. I for inference. Okay, let us see this. Okay, again, the idea is this, that maybe you are given a text which is called premise. You have a hypothesis, and then you have to say whether hypothesis entails the premise, contradicts the premise, or it is neutral to the premise. Okay, in this case, it is what? It is entailment. Right. Let us see this. So SST2, if I see, we have talked about IMDb. Now we are talking about SNLI, right? All these three are created by some set of people from Stanford. Okay, so and this is how it looks like. Again, this is very important to see how the data set actually looks like. This is not how you have used it in your training. This is your premise. This is your hypothesis. And then 5 annotators, 5 independent annotators were employed to give labels. Right. For this particular pair, for the first pair, you see all these 5 people have said C. That means contradiction. Right. And then you take the majority label. So again, all 5 have said C, so majority label is C. Okay, what you do in your ML, or what you do in your actual fine tuning in your kind of deep learning things, deep learning task or task classification models, you actually just use this final label, right? You don't use this individual C, 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 C. to train your models, right? You use this final majority label, but this label is also available. The fine grained labels are also available. Okay. You talk about the second instance here. An older and a younger man are smiling. Now the hypothesis is two men are smiling and laughing at the cats playing on the floor. Okay. Out of 5 annotators, 4 said this is neutral, 1 said that this is entailment. Okay. Majority label is neutral. Yes. So it is like, so like if you just employ maybe just one annotator, there is a high chance that that annotator is biased. That is one possibility. Is not knowledgeable, right? That is another possibility. The other could be that it just that annotator maybe is not in a good mood, right? It's making all the labeling wrong. That's possible. So ensembling, it is at the end some sort of ensembling that we are doing on the labels. Okay, so averaging out makes that error lesser probable than it was before. Okay, the problem with this kind of approach is you require huge funds and time and good set of people. Right. So that is the major bottleneck here to create these kind of data sets. Right. Even if you see here, so if so let us see how many instances it has. I don't exactly remember. So see, it has this many number of English sentences, 570K, right? Each sentence pair is annotated by how many people? 5. Each annotation takes at least half a minute. You see the time spent on this task. And then you are paying these people. You are paying some dollars for each annotation that they are making, right? So it's a huge investment of both time, effort, and money, right? And that's why like getting a labeled data set is more difficult than getting trained models these days. Okay, and we'll see examples where all the kind of good data sets are only available for English. Do you remember any good data set in Hindi? Have you seen any good data set in Hindi? A very good data set which is labeled good quality in Hindi and created by some Indian. Right? Try to find out some good data sets. Right? You can find out a lot of, like you name any benchmark, you will find out that that is being or that is created for English. Right? So that is the problem. That's actually is the problem. Fine. Okay. Let's move to the next one. Then the third task is named entity recognition. How many of you have used this Connell dataset? You have used the Connell dataset before? Okay. Okay. Anyone else? Okay. So what is Connell? You have used the dataset, I know. What is Connell? Have you heard this name Connell before? You have used it in a hands-on, but do you know what is Connell? Why I am teaching all this is because you should not kind of just spend time on modeling and kind of using the data sets and the code which is already available, right? You should know the entire picture. So what is Connell? Conference on Natural Language. Okay. Okay, again, not asking for the full form here. So maybe what exactly it is. So Connell is a kind of a venue which hosts a lot of shared tasks. Right. So shared tasks are very common in NLP community. So when I say shared tasks, these are like hackathons. Okay, again, more difficult than what we had yesterday. So these are more research-driven hackathons, shared tasks, right? Where they will come up with some new data set. Okay, and people have to compete on that data set to get the best scores. Okay, so this named entity recognition data set, this very popular one, is not Connell kind of a data set. It was proposed as one of the shared tasks in Connell 2003, and it became popular after that. Okay, so I'll just click on it. I'll just see what exactly it is. And what is named entity cognition? Don't look for the answer here, so, but it is there here. So what is named entity cognition? No. What is an entity? Proper noun, common noun. So okay, fine. Yeah. Okay. Anything? Any other answer? Can you give me some names of entity? Whatever you are saying is type. Person is one sort of entity. Organization in another location is third type of entity, right? And then there can be some symbols also. For dollar is related to money or funds, right? So these are all different types of entities. Okay. So the task here was the following. Again, I'm kind of right now talking about the shared task, Funnel 2003, right? And if you see here, what it wants is the following. Suppose your sentence is this: United Nations official heads for Baghdad. That was your sentence. UN official heads for Baghdad. And you have to identify what are the named entities. You have to first identify the entities, and then you have to assign a label to them. This is kind of a two-stage classification task, right? So in the first stage, you have to identify which are the named entities. And once you have identified those named entities, you have to assign a class to them. Okay. So here, for example, United Nations is what? It is an entity and it is of type organization. Okay. Official is not an entity. Okay, we'll leave as it is. Then this person, official EQS, probably this is the name of that person, official. So what is its entity? So this is PER, person. Okay. Then heads for Baghdad. So Baghdad is another entity, the third entity present in the same sentence, and its type is LOC, which is location. Okay. And at that time in 2003, the task was very simple, that you have to just identify the entities and associate their labels. Fine, that was the task. And it became very popular. So, okay, this data, it talks about how this data was created. Okay, and that's all, right? So again, this is not very important, but yeah. And these were the results for that shared task, right? Again, the models are doing almost like reaching almost 100% on this data set, but this was a snapshot of 2003. Okay, so precision, recall, F score almost 88%. And these are different papers which were submitted, which were computing at that time. Okay, so this was for English. It was proposed for two languages, English and German. For German, again, these were the kind of scores. Baseline was poor, right? Baseline was around 71, but almost all models have done better than a baseline. Okay. So again, this is whatever I'm talking about is not the exhaustive list of all possible benchmarks dataset which are created for NER for sentiment. These are just the representative ones or the popular ones. Okay. Then for part of speech tagging, we have another very popular dataset. So what is part of speech tagging? PS tagging? Noun, verb. So given a sequence of tokens, you want to assign some labels to them. These are the part of speech like noun, pronoun, verb, adverb. Okay. How many part of speech you have been taught in your elementary school? 8. Can you name them? Interjection. Okay, so how many? Okay, anything that is left? Determiners? So how many you were taught? Okay, so we're talking about that thing. Okay. Here the things are more complicated. Nouns can further be subdivided into multiple types of pure stacks, right? So these are subcategories of noun. Similarly for pronoun, for preposition, and so on and so forth, right? So that is there, right? What I want is this. So this is again very popular data set, which is called PTB, Penn Tree Bank data set, which is the most popular data set used for POS tagging classification task. Fine, I don't know if you have seen it before. How many of you have seen this data set before? If you have done these tasks, not many people don't use these things these days, but this used to be very popular. Okay, so Penn Tree Bank. Why this is called Penn? Because it was proposed by University of Pennsylvania. Okay, great. I'll just show you what are the different categories. It has total 48 tags. 48 tags that can be assigned to each of the word that is going to appear. Right. And if you see whatever you have said is true, the major categories are anyway there, then subcategories are also there. Okay. They have created, okay, so these are 36 POS tags and 12 other tags. I can see that. What they have done is, I don't exactly remember the size of this data set. It is in thousands again, but all this was done manually by humans. That's why they can create this data set, benchmark data set, right? You train your models and then you compare it with the humans. Okay, and you can imagine the efforts that were put to create this kind of data set. Each word will be annotated to one of the 48 different categories, right? Again, creating, again, this is for English. I don't know if there are some for Hindi. I think there is one for Hindi that was created by IIT Bombay. So Professor Pushpak team has done very good amount of work in POS tagging and basic NLP, the traditional NLP. He will be arriving today. He'll be talking tomorrow. So his team has created very nice set of benchmarks for Indian languages, and similarly, like for English, for Hindi, he has created one such data set. Fine. Okay, there are a few more. So again, if I talk about the modern NLP, the NLP that you're seeing these days, so sentiment analysis is still used. People are still using these models for sentiment analysis, right? People are also actively using SNLI, inference tasks, right? NER, it is not very popular these days, and POS tagging is again considered as a very solved problem. So not very popular these days. Okay. Now we'll talk about another very interesting task, close-end task. This is called co-reference resolution. Right. So it is again one type of capability which we want to see whether models have this capability or not. Okay. The example is, just read this input sentence, and then there are two underlines. Right. So the first sentence is Mark told Pete many lies about himself, which Pete included in his book. He should have been more truthful. So then there is one underline at Pete, and the other underline is at he. Right. The question is this pronoun referring to Pete? The pronoun he is referring to Pete. Now, if this is yes, you say, if you think this is correct, you say true. If it is not correct, you say false. Right. The label is false. He is actually referring to Mark, not Pete. Right. We want model to have this capability. Right. And this type of task is called co-reference resolution, where the pronouns will refer to some nouns which have appeared before. Right. We want to see if the model have an understanding whether they are referring to the correct pronoun or not, or the pronoun is referring to the correct noun or not. Okay, this is the task, co-reference resolution, and again the very popular data set is this one, WSC. Maybe one of the benchmark that was shown last few days back. It has this, the model was tested on WSC dataset. Vinograd schema challenge. Again, this is a common sense knowledge data set. Okay. How many total instances are there in this data set? Just 150. So all these big language models are actually tested on these 150 data sets, points, instances, right? And then and all these instances are available. So probably while these models were created, at that time they have already seen this data set. So whenever you test those models on these kind of tests, they have already know the task. So that's why they do very well on these tasks. Okay, so this has been very popular. Originally, this data set was proposed for English. Later, people have translated the same task for other languages. So for Chinese also it is possible. For Hindi, I guess also it is possible. Again, you see the translation into French, Portuguese is there, Chinese is there, Hungarian, Russian, Thai. So these are the known ones. Again, very recent efforts have also happened for Hindi. For Hindi translation also. Again, translation is not a difficult task, right? You use any translator, English to Hindi, it will do it for you, right? But yes, these are available. Okay, fine. But the idea should be clear. What does this WSC represents? Vinograd schema challenge. It's a common sense reasoning task where we want to check the capability of a model, whether it understands the pronoun, the association between the pronoun and the nouns very well or not. Okay, and then comes this question answering task, which is question answering capability. So very popular, the most popular is this squad data set. Who proposed squad? Stanford. Okay, so most of these very popular data sets are proposed by Stanford. Okay, let us see this data set also once. Okay, it looks like this. So you have some passage, the passage is here, and then there is one question, and then you have to find out the answer in the passage. Why it is not a generation task? It looks like a generation task, right? Why it is not a generation task here? Where? So even though we are taking the answer from the passage, but that is also some sort of a generation. So model does not actually the way the benchmark works is it does not create the generation, the textual generation. It just creates the span that this is the beginning of your answer and this is the end of your answer. Right. So it is again a classification task. For each character, it just says whether that character is a possible answer or not. Right. So wherever your answer is going to begin, it will say that this is the start of your answer. And then the next set of characters will be the part of the answer. And wherever your answer ends, it will say this is the end of the answer. So it is again a classification task. Squad at least. There are other open-ended classification question answering things, but this is close-ended. Right, you have the kind of okay, and this is how the squad looks like. The squad benchmark looks like. Squad was proposed in 2019, I guess. Squad 2 was proposed in 2019. Just check once. No, it was proposed in 2018. Squad 1 was proposed in 2017. So within 1 year, the models were proposed and they have reached almost 100% for squad dataset. Then they came up with a newer version of the squad, which is more challenging, and that was like the next year, 2018. They came up with a new one, and this is what is the leaderboard right now looks like. Almost we have reached 90% on this dataset also. What are the top models on this dataset? All these are ensemble models. Right, so see this one. This is ensemble model, this is ensemble model, this is also ensemble model, this one, this one, this one. All these are mostly ensemble models, which are at the top ranks. Right, so classification tasks, most of the times you see their, yes. So you just click on it, they will tell you what exactly is ensemble. right? So there are multiple models which are trained, and then they are just kind of ensembling their outputs to get the final this thing. Okay, so different teams have different ensembles for different type of models. Okay, but that is how it is. So all these are not just one model which is giving you the correct output. It is like the multiple models. You are getting multiple outputs from each of the model. Then you are aggregating those outputs to generate the final output. Okay, this is good, right? So this was proposed in 2018. Yes. Yes, yes, it is possible. That's what I said, that leak can happen. Yes, no, they don't. So we'll talk about that in detail. Right. So this is just an introduction to all sort of things which are all sort of benchmarks which are available. Then we'll also talk about challenges. Right. But you should see this benchmark. At least you will remember this benchmark in your that you have seen them before. Okay. Whenever you'll talk about them next. Yes. Because for the classification, see, so let's not talk about the deep learning era from like 2014 or 2012. Before that, whenever you were talking about any sort of classification task, which type of models you used to pick? Decision trees and then its variants, which are the ensemble models, right? So it's the same thing that is happening right now, but it is more on the neural network side. So you have multiple neural networks, right? And then you are ensembling their predictions. So all these are neural networks, different type of neural networks, right? But not those decision trees. Yes. Which one? That I am not very sure. That I'm not sure. I think here what they are trying to do is they have trained multiple different neural networks, and then they have combined the neural networks through some sort of another weights, right? And then that weight is aggregating this thing. So it is not kind of a hard majority voting that is happening. So it's kind of all the predictions are happening. They are joining all the predictions through one weight, one more feed forward layer, and then whatever it predicts is actually your final output. Right. So again, this is more on the neural networks actually, not the way the traditional ML used to happen. Okay. Why I wanted to show is this. Yeah, this is here. The first one. Just see the human performance. The first row. The human performance on the test data, if you see, was around 86 and F1 was 89. And the models which are at the top of the leaderboard, they have already surpassed the human performance. Right, which is very interesting. I'll later explain why, even though they are surpassing it, but in real scenarios it doesn't happen. They are actually that good, but yeah, on the leaderboard it looks like that. The models are actually surpassing human performance also, right? So the models are becoming kind of superhuman intelligence. They are displaying that property. But yeah, it is the case. Okay, fine. So this was about question answering and about very popular squad data set. Okay, then we have some more benchmarks. One benchmark is called glue, and then its uh, next version was called super glue. Right. Again, these are very popular. All the current language models, whichever you see, are they evaluate themselves on these benchmarks, glue or super glue. Okay. How many of you have seen what is a glue benchmark? What is a super glue benchmark? Have you seen this before? Okay. At the end, why models are trying to evaluate themselves on these benchmark is to just see whether they have the human-like capabilities or not, right? So that means these benchmarks have some sort of tasks which measure some sort of human capabilities. right? So okay, again we'll see what are those, but see this first figure is from glue and the second figure is from super glue. Okay, I'll just visit glue and then I'll also visit super glue once. So how to read this benchmark? Any idea how to read this benchmark? How to read this table? Let me say it in a more simpler way. What are these? Different types of models which are submitted, right? And this is the name of the model. This is the name of the team. This is the name of the model which each team has proposed. Then this is a link to the paper if they have submitted some paper along with the submission. And then these are different tasks. So COLA is one task, SST2 is another data set. So again, these are different data sets, right? COLA is one. And then SST2 is another one, MRPC is another one, STSB, QQP, ML, NLI, and so on and so forth, right? So these are different data sets. And for each data set, the model has performed some and it has given some values, right? If you see again here, almost all models are above 90, right? So they are kind of doing very good on glue. This is more difficult benchmark. I'll explain why it is more difficult, right? On this more difficult benchmark also, the results are almost similar. Most models have reached almost 91 that they have kind of reached for all sort of data sets. Fine. So yeah. Okay, let us go back. So these are the different data sets that are present in superglue. So one is called AXB. This is broad coverage diagnostic. So this is some sort of a medical data set which is there. Then what is more important is this kind of the data set. This is COPA data set. This is BoolQ data set, right? Again, different data sets are going to capture different capabilities of a model. So what does this each look like, right? What are the capabilities we are looking for? So maybe this is kind of a bit blurred. So let me see what I can do. Can you read it now? No? Oh, that's difficult. Now I think this is better. Okay, so in BoolQ, one of the data set on which superglue is based on, it captures this capability, the question answering capability. So you are given a passage. This is the passage. Then you are given a question, and then you have to answer either yes or no. So it's a Boolean question answering task. Right. So it is a reading comprehension kind of a capability that we are looking for to have in the model. Then this CB is again analyze type of task. You are given some passage or premise, you are given some hypothesis. You have to say whether the entailment is happening, not happening, or it is neutral. Right. And then you have this COPA data set. COPA is more on the causation side. So the premise is this one: my body cast a shadow over the grass. Okay. The question is, what is the cause for this? Alternative one, or the option one, is the sun was rising. Alternative two, the grass was cut. And then the model has to pick one option out of these two. So this is more on the cause effect analysis, right? The model should have that kind of capability. Okay, so these are again, I'll not talk about all the data sets, but this is how it looks like. Okay, so these are different data sets that are there in superglue. Okay, so we have seen few things. We have seen the close-end tasks. We have seen multiple such different types of close-end tasks. We have seen the data sets available. We have also seen some benchmarks, right? All these things we have seen, but let us talk about some challenges. Okay, so for each task, what is going to be your metric? right? So some people have chosen accuracy, some people choose precision, some people choose recall, right? Some might say, no, accuracy is not a good metric. Let us choose precision, or maybe we choose exact match, and so on and so forth, right? So which metric needs to be chosen for which task is again very debatable. Okay, and again we'll see why that can create a problem. Then if suppose in case of super glue you have 10 tasks, right? My model is doing good on 7, it is not doing good on 3. The other model is again doing good on 7 but not on 3. Again, the set intersection is non-zero. Okay, so that means how to aggregate the performance on different data sets, right? So it is like just equal weightage should be given to all the data sets that are there in the benchmark, or we assign some sort of weights to each of the data set that are there in the benchmark. Okay, right, the final score based on which the ranking is going to happen. Third is, where do the labels come from? Again, if some benchmark has been created and not very good set of annotators were employed to create that benchmark, maybe our model or maybe our data set has a lot of noise or a lot of issues related to labeling. Okay, that might not be a good idea. It might not be a good idea to use that data set for any sort of modeling. Okay, and finally, there can be some spurious correlations. So correlations might not occur, but model might have learned those correlations to provide you the responses. We'll see some interesting use cases. Okay, fine. So let us see some ways to evaluate classification performance. Okay, so how will you do that? How will you evaluate whether a model is a good classification model? You have to choose a matrix. What are the popular classification matrix? Precision, recall, and F score, F1, and accuracy. That is also possible. These are common ones, right? Precision, recall, F score, accuracy. Okay, we'll do some hands-on now. Suppose you are given this sort of a table. Okay, what is this matrix called? Confusion matrix. Some of you know that, right? So this is called as confusion matrix. Let us try to read this confusion matrix. So the problem here was that I have some documents. Maybe let us talk about, suppose I have some Wikipedia articles, right? And I have passed those Wikipedias again. So different articles belong to different categories. So some articles belong to, maybe they are talking about United Kingdom, right? So some articles are about UK, some articles are about poultry, some articles are about wheat, some are about coffee, some are about some sort of a loan interest, right? Some articles are about trade. These are different topics which are assigned to each of the article that was there in my corpus. Okay, I trained a model which is a topic classification kind of a model that you pick. I'll pass you one article and you have to assign a label to it out of these 6 labels. Okay, then what is done is the following. For the articles which were true UK means all articles which were assigned the real UK class, right? Out of those articles, 95 were actually assigned UK by the model. One was assigned the poultry class, one was assigned the wheat class, 13 was assigned the wheat class, 0 articles were assigned to the coffee class, 1 article was assigned to interest class, and 0 were assigned to trade class. Right. So this is just the prediction from some model. Okay. Again, articles for poultry, no article from poultry was assigned to UK. 1 poultry article was assigned to poultry class. 0 were assigned to wheat, 0 were assigned to coffee, and then 0 and 0 for interest and trade. Right. Same for wheat. So for wheat, 10 wheat articles were assigned to UK, 90 were assigned to poultry, 0 were assigned to wheat, and so on and so forth. Right. So this is how you read the confusion matrix. So your row is the real labels, and the columns are your predicted labels, right? Again, you can exchange the rows and columns, that is up to you. But this is how the current this one looks like. Okay. So how will you calculate the precision of this model? Can you calculate the precision of this model? Yeah. What is a true positive here? Sum of diagonal elements. Those are the True positives. And then what will be in the denominator? True positives and then false positives. So what are the false positives here? Some of the elements which are not under diagonals. Okay, so someone is saying that to calculate precision, we have to sum in the numerator. We are going to have sum over the diagonals, and in the denominator we have all the non-diagonal entries, the sum of over the non-diagonal entries, right? Sum of all the elements. Okay, how will you calculate recall? Because you have to calculate precision recall, right? Okay. So how will you calculate recall then? Okay, what is the false negative here? What is that false negative here? That is what your model outputs gives you, right? False negatives, true positives. It gives you accuracy, it gives you precision, recall, and then it calculates the F1 scores, right? So what about how do you do it here? This is a very simple example, toy example, right? How will you do it? Just take out your pen and papers. Maybe let us do some exercises. You have done it before, right? This is just a kind of a exercise that we're doing. You have done it for, so just remember one thing, whatever you have done till now, or maybe you have practiced with your hand is mostly for two classes. There it is easy to define what is true positive, true negatives, right? False positives, false negatives. Here we don't have two classes. We have many classes or 6 classes. Have you heard these names like called, which are like micro precision, macro precision, micro recall, macro recall? Do you know when to take what? No? Okay. Okay, we'll see. Before that, you do this. Maybe this is easier problem than doing that. Just try to read this. This is more sort of an easy problem, and yeah, just read it once. Again, a very tricky one. We ask this problem in our PhD interviews. If someone we are interviewing is for ML. Pardon? It is a distribution. It is a distribution which is biased. That's what it says. It is a distribution which is biased. So I'll just read it for you. Okay, so we have a classification data set. Any classification data set is fine, which has two classes, P and N, right? But the data set is heavily biased towards P class. So 99% instances are from P class. Just 1% instances belong to N class. Okay, now we randomly sample two subsets from this. I call one subset as train, I call the other subset as test. That is how we do, right? In our real implementations also. We train a BERT model on train subset. Okay. However, due to poor training, the trained model predicts P always on test data set. Okay. So what is the accuracy of this model? The accuracy of this model is how much? But is this a good model? A model with a 99% accuracy, is this a good model? First of all, how many of you are saying that this is 99%? How many of you are confident that the model is 99% accurate? How many of you think it is 100% accurate? Yes. It is proportional. It is proportional with respect to the original proportion. So it is the answer, correct answer is 99%. The model is 99% accurate, right? That is correct. Why this model is not a good model then? Hmm? The performance for the class n will be very bad, and possibly n was the class where we were interested. What kind of task we are looking for here? Maybe cancer detection, maybe fraud detection, where most of the instances are normal instances, few of them are abnormal instances, right? So even my model is 99% accurate, but my model is not good. So that means accuracy might not be a good idea. Hmm? Recall is a good idea. Okay. Precision will be a good idea. Okay. We'll see on this. Okay. But accuracy is not a good idea. The way we have defined accuracy till now. Right? Okay. What is the accuracy of the model with respect to label 1, label P? What is the accuracy of the model with respect to label P? 100%. What is the accuracy of the model with respect to label N? 0. So what is the average accuracy? 50. Simple. Let us keep it very simple. It is how much? 50%. Let us use this kind of accuracy. Right. So again, this is a very simple way to kind of give an counter example where like your model is very accurate, but it will not do good in real scenarios. And then maybe instead of changing the model, we change our metric to show that actually the model is bad. Right. So this is kind of so whatever we have done before was more at the micro level. We just have picked all the instances in the training, in the test, and we have calculated the accuracy over them. Right, that's called the micro performance evaluation. Whatever I did later was more the macro side. I calculated the accuracy for P, I calculated the accuracy for N, and I just did a simple averaging. Right. So not always you should prefer micro. Most of the times, whenever you use sklearn, sometimes many of you use sklearn, you should be very careful what implementation of sklearn metric you are using, whether this data set is very biased or not. If the data set is very biased, don't go for micro metrics, go for macro metrics. It has an option for that. Okay, I have given you some idea. We'll again. Okay, so we'll again see here. Okay, so I hope you got some idea, right? So what is how will you define precision? Okay, let us keep it simple. So what is the precision for class UK? Instead of giving you the final precision, the overall precision, what is the precision for class UK? How will you calculate the precision for class UK? Hmm? So what will be the number on the numerator? 95 will be on the numerator, and what will be on the denominator? Hmm? 95 plus 1 plus 13 plus 0 plus 1 plus 0, or it will be 95 plus 0 plus 10 plus 0 plus 0. What will be there on the denominator? You use your learnings that you have done in your ML class, right? I'm not confusing you. Just use that. What is the true positive for UK? All documents which were UK and predicted as UK. What is the false positive for the UK class? All documents which were assigned the class UK. But they belong to other classes. Right. So we are going to sum over the row or sum over the column? Column, right? So the precision is 95. Precision for UK is 95 divided by 95 plus 0 plus 10 plus 0. Again, this dash, just ignore it. Keep it as 0. 0 plus 0. Okay, precision for wheat will be what? Precision for wheat? Precision for wheat will be 0, right? 0 divided by the entire column, 13 plus 0 plus 0 plus 0 plus 2 plus 2. Okay, fine. Okay, what about recall? What will be the recall for class UK? 95 will be in the numerator, that is correct. And then what will be in the denominator? Summation over the row, the first row. That is going to be your recall. Recall for class UK. Same you can do for poultry, right? Same you can do for wheat, coffee, interest, and trade, right? All these scores, whatever you have done, are called macro precision, macro recalls. Macro precisions, macro recall, right? Once you have done it for all the classes, you just take an average over them. That will be your final precision of the model using the macro method, right? And the final recall using the macro. For micro, how it is done? Just look for the document. Whether they actually do it, the micro, in case of so many instances or so many labels, just try to see the SQL and implementation, you will get an idea, right? But the macro one is done like that, right? What is F1? Harmonic mean of precision and recall, right? So that is just the harmonic mean of, so 2 into P into R divided by P plus R. That is one implementation. Again, F1 has multiple implementations, right? Most popular is this F1. Okay, fine, great, yes. So again, there are different models, right? And there is a trade-off between precision and recall in most of the models, right? So it is that particular point in the model performance where you are getting a decent precision and decent recall. Okay, and this is one of the way as a researcher we find out if you have actually written correct, you have actually done some experiments or not. Most of the times, if your precision, if your recall, sorry, if your F score value is between precision and recall, then only we know that yes, these experiments are real. Sometimes people make numbers and they will put, they'll keep their F scores higher than precision and recall, which cannot happen. Right. So because this is a harmonic mean at the end. And we have seen papers like that. We have seen papers when we review that numbers are made up. So it should be harmonic mean. Even if you're making numbers, just make that number as a harmonic mean of P and N. Okay, and add that in the paper. Okay, fine, great. So that is what the next slide talks about. We are calculating precision. We are calculating recall. Okay, and then we also talked about the way we used to calculate accuracy before, but that might not be a good case, right? So it can be biased towards the very popular class. So we need to be careful for that. Okay, so this is one problem, right? So one problem or one challenge here is given a task, which matrix I have to propose, right? Macro ones, micro ones, whether precision recall will work or not, right? Whether accuracy, I should report accuracy and so, right? So that decision you have to make. The second problem that you will find in many of these classification model is this spurious correlations. Okay. So just read this particular, the second one. Spielberg is a great spinner of a yarn. However, this time he just didn't do it for me. Prediction is positive. This is a sentiment analysis model. Is this a positive sentiment? No. But it is predicting it as a positive. Why? Because of the grade. Okay. In the paper, it was shown that whenever this name appears, this particular name, it is going to predict it as a positive. The model was trained like that. All right. So it was kind of an associating this particular feature, which was the name, with the label. Whenever this name is going to appear, whatever is the sentiment, doesn't matter, it will assign it as a positive class. Right. Same thing can happen in the other way around also. See the next example. The benefits of the New York subway system is that a person can get from A to B without being stuck in traffic, and subway trains are faster than buses. The model was trained such that every time whenever it is now saying this New York subway, it is going to predict that as a negative class. Why this is possible? Why do you think model has learned such spurious correlations? Yes, right. So in the training data, wherever this word, the first word Spielberg or it was appearing, all those sentiments were positive. The model might have learned that whenever this word will appear in future, the sentiment is going to be positive. Okay, and the other way around for New York subway. Okay, so this is kind of one sort of spurious correlations that can happen, right? Other is this. So again, so is this a important feature while deciding the sentiment of a sentence? Right. So these kind of spurious features are called irrelevant features. Right. They are there because you have to make the sentence grammatically correct, right? But they actually don't contribute any to the sentiment of a particular sentence, right? So the problem is the sentence is going to have these words. It is very difficult to train a model and train it such that it should not attend to these spurious features, right? So because they are going to be there. Okay. So these are irrelevant features. Then there are some necessary features, but not sufficient. For example, read this sentence. The differential compounds to a hefty sum over time. The differential will not grow. The differential will grow. Let's talk about the word not. Not itself does not carry any sentiment, right? But not will be associated with other features to decide the sentiment. Okay, so it is necessary but not sufficient to decide the sentiment. Okay, again, this kind of features are part of or can be called as some spurious features, which can occur or usually occur. And this is very difficult to kind of get away with these sort of features. Okay, so we'll talk about open-ended evaluation now. Okay, so so when we talked about open-ended evaluation, we mapped it with the generation tasks, right? The way that is how we announced these this open-ended evaluations. So there exist or there are three types of evaluation schemes here. One is called content-based content overlap-based matrix, right? So where maybe you have generated something, the model has generated something, and then you want to compare that generation with the expert generation. Okay, so this is called content overlap metric, and there you want to see whether the words or the tokens which are present in the expert summary or expert generation are also there in the model generation or not, right? So just a token overlap kind of a setup. Then you have the second type of evaluation, which is model based metric. So maybe you are passing generated text to another model, and that model will decide a score or is going to assign a score whether this is a good generation or not. Okay, and finally we have the human evaluator. So maybe you have humans which are going to evaluate the generations. Okay, which one of them you think is the most costly? The last one, where humans are there in the loop to evaluate your generations. Okay, so we will see some content overlap matrix, and then we'll also talk about model based metrics, and then we'll move to human evaluations, and we'll see what are the major challenges there. Okay, so the idea in case of content overlap matrix is the following. You have some reference sentence. So reference sentence is maybe this is a sentence which is created by some human, some expert, right? And the sentence is they walk to the grocery store. And then maybe corresponding to this sentence, the generation from the model is the woman went to the hardware store. Okay. Now what I want is that I want a score that kind of finds out the similarity between these two sentences. Okay. And if you see here, and this is more at the lexical side. So when I say lexical, this is more at the token overlap. The tokens in the reference generation is same as the tokens in the model generation. Okay. So this kind of evaluation is very fast, right? So you have a set of questions or maybe set of input pairs where you have a input and the output, the expected output. Then you are passing all these inputs to the model generates, and then you compare it with the actual the actual output that you have, right? Again, this is a metric, some sort of metric which is fast, efficient. No human is required in this loop. Everything is just one time. You have maybe employed some annotators in the beginning when you created that ground truth data set. Right? Now you don't require when you are going to evaluate these systems. Okay, so there are some very popular metrics, and these are n-gram overlap metrics. Blue Rouge. Possibly you have heard at least these two names. Meteor is again a very popular metric, but not as popular as Blue. So where do you use Rouge metric? For summarization, for evaluating the models which summarize text, right? And Blue for machine translation, right? So Blue is a metric which is popularly used in machine translation, and Rouge is used to evaluate systems which summarize. Okay, but again, you can interchangeably use both of these metrics. That is also possible. Okay, we'll see what is the difference between. Again, I'll explain Rouge, but again, the same way you can also describe Blue. Okay, but these are two metrics which can be used for automatic evaluation of generations. Okay, Blue is precision based. Rouge R stands for recall. So this is a recall based matrix. Okay, and that is how we define Rouge. Okay, so again, a very complicated formula. I'll explain what exactly it is. So Rouge stands for recall oriented understudy for gisting evaluation. It is a metric for automatically evaluating summaries. It's not good as human evaluation, but again, human evaluation takes a lot of effort. So it is good if you don't want to spend that much amount of effort for evaluating summaries. Okay, the idea here is the following, that you have some document D and you have a automatic summary X, right? Now have n humans produce a set of reference summaries of D. Okay, so you have one automatic summary X. You have generated this X from some model. Okay, for the input document D, and then you have also employed n annotators, n humans, which are going to generate n number of reference summaries for D. Okay, and you want to find out how much is the overlap between X and those n summaries. Okay, Rouge is what it calculates. Okay, so this is a Rouge bigram, Rouge 2. Rouge 3 is also there, where like you want to see the overlap between the trigrams. So bigrams means consecutive tokens. Okay, a pair of consecutive token constitutes one bigram. We'll see that in the next. But 2 means bigram. If it is Rouge 3, then that means trigram. Okay, so what we want is the following, or how this Rouge is calculated is the following. In the denominator, just read the denominator once. Just read it. It's okay. Don't understand it. So in the denominator, you have what? All the bigrams, all the count of all the bigrams that occur where? In the reference summary or in the generated summary? In the reference summary. All right. So in the denominator, it is the count of all the bigrams that occur in the reference summaries. Okay. What do you have in the numerator? Count of all the bigrams which were there in the reference summary and are present in the generated summary. Count of all the bigrams which were there in the reference summary and are also present in the generated summary. That will be in the numerator. So denominator is like the count of all the bigrams that are there in the reference summary. numerator, it is the count of all the bigrams which are there in the reference summary and are also present in the generated summary, right? And this is why if you see, this looks like a recall. That is how we define recall, right? So this is why this metric is recall based metric. We just want to find out we just want to find out what is the proportion of all the bigrams which are there in the which are there in that in your expert summaries are also there in your generated summary or not, right? So given this, suppose you only have this time one reference summary, not multiple, not n reference summary, just one, n equal to 1 here. Okay, so you have the automatic summary, the cat was found under the bed, and the reference summary is the cat was under the bed. So what will be the Rouge 2 score here? Can you calculate the Rouge 2? What will be the bigrams in the reference summary? So what is the first bigram? The cat is the first bigram, then cat was is the second, was under the bed. These are the bigrams, right, in the reference summary. And what are the bigrams in the automatic summary? The cat was found under the bed, right? So these are the generated summary bigrams and reference summary bigrams. Just check if they are fine with how we have defined the bigrams. Right? Is this okay? Okay. Now what will be the Rouge 2 score? What will be in the denominator? So in the denominator. No, but the value, what will be the value in the denominator? 5? 4? Okay. 5. Okay. What will be in the numerator? 4? 6? So you just have to see how many bigrams that are there in the reference summary are also present in the generated summary. So how many such bigrams are there? So the first bigram, the cat is there, right? Second bigram, cat was is there, it is also there, and then was under is not present, under the is present, the bed is present. So 4 bigrams are present, right? Which were there in the reference summary. And if you calculate this Rouge 2, it is going to be 45. Is this okay? Right? You can expand it to Rouge 3 also. Rouge 3 is nothing, it is just trigram overlap. Right? So Rouge 2, Rouge 3, Rouge 4, all these are common. Yes. We have not considered that in implementations. Yes, they do consider, but for this example, we are not considering. We are not adding or appending or prepending any start or end of the token. Right. So here it is just the first word is the start of the sequence. Okay. So Rouge 2 is what we have seen. Then there are other variants of Rouge. Rouge 3 and Rouge 4 are also there. Then Rouge L is there, and then Rouge S is also there. So L means what is the longest common subsequence in or longest subsequence in the reference summary, which is there in the generate summary. Right. So again the formula differs, but that's the overall idea here. S is skip unigram Rouge. So what does this means is so suppose in your reference summary you have the cat was under the bed, and in the automatic summary you have the black cat was found under the bed. The black cat was found under the bed, right? And if you create bigrams, it will be the black cat, right? So here, if you just skip the black, then you have the word, the bigram, the cat, which matches with the reference, right? So here, in case of Rouge S, you can have you can kind of introduce some errors. It is okay to have some errors, right? Unigram errors. Maybe some words are introduced, and that is why you are not able to find out some bigram. But those errors can be considered. Okay, so then again there are other variants of Rouge also, but most popular one is Rouge N, where N can be 1, 2, 3, 4. Till 4 is popular. Okay, let us consider a simple failure case. This is one example where you have two sentences. The quick brown fox jumps over the lazy dog. A speedy fox leapt over a sleepy canine. The two sentences are semantically same, or I should say similar, right? But if I compare or if I calculate the Rouge 2 scores, that will be what? 0, even though they are very similar, right? So that means these kind of content based overlap or bag of word based overlap metrics will not work in scenarios where like the words are semantically similar. And this is one such example. It is almost similar. Like if you find out actual similarity is more than 0.9, but the lexical similarity is 0 here. Okay, what is the unigram overlap here? Just if you talk about the unigram overlap, like number of unigrams which are common in both of them. 2, just 2, right? Bigram overlap 0, right? So that is kind of almost 0 lexical similarity, right? But semantic similarity actually very high. Okay, so this is where new types of models have been proposed. Again, I should not talk about this. I should first talk about BLUE, but I don't have that in here. In case of BLUE, what you have is BLUE is exactly same as Rouge, right? So Rouge is based on recall, BLUE is based on precision. Okay, so what you are going to do here in case of BLUE is you will change the denominator. In case of BLUE, what will be the denominator? You will find out all the bigrams which are there in the generated summary. That is going to be your denominator, right? All the bigrams, count of all the bigrams that are there in your generated summary or generated translation. That will be your bigram. That will be a denominator. The numerator will be what? Count of all the bigrams that are generated and are also present in the reference translation reference summary. Okay, so BLUE is precision based metric and Rouge is recall based metric. Okay, that's the only difference between BLUE and Rouge. So you can also use BLUE for translation or for summarization, and you can also use Rouge for translation. That is what you can always do, right? But again, the way they were proposed, that's why they become popular. So Rouge was proposed for summarization, so it became popular for summarization over the time. Yes. Because that is how they were introduced, and that's why they become popular. So these days, like you can use any of these for any of the case. Okay, so then so that means like whatever we have seen, so unigram or bigram overlap based matrix might not work well. Okay, so this is where model based similarity matrix have been proposed, right? Where the model based embeddings maybe or model based or some architectures will provide a kind of a similarity score. We'll see what I mean by that. And based on that similarity, you decide whether these two sentences are similar, these two passages are similar or not. Okay, so this is where I'll talk about 3 different techniques. One is based on what is called vector similarity. Then we have a BERT score, and then we have one more architecture which was proposed later. Okay, so what it says is the following. So vector similarity, the idea here is very simple. And then there are 4 papers in vector similarity. One is called embedding average. The second one is vectors extrema, MEND, and YISI. Okay, almost again, these are kind of a bit old paper, at least 5-year old papers. So in case of embedding average, what they do is the following, that suppose we have 2 sentences, right? Suppose we have 2 sentences and we have some embedding model. you know some embedding word, right? BERT can be used as to generate embeddings for each of the word in the sentence, right? So suppose you are passing a sentence through the BERT, and the top you will get one embedding vector for each of the word. Okay, that is possible. You pass the second sentence also through the same BERT model, right? Again, you will get at the top one embedding corresponding to each of the token, input token, right? Now what you do is you just take average over all the tokens for the first sentence. Again, you take the average over all the tokens for the second sentence. What that will give you? One vector corresponding to the sentence 1 and one vector corresponding to sentence 2. Then you find out the cosine similarity between them. That can be one way to find out the similarity between two sentences. So, and this is more the semantic side, right? And that is this first model, this first idea, embedding average, talks about. Okay, fine. So idea is simple. That again, I'll just repeat it once. That you have two sentences. You pass these two sentences through BERT. BERT will generate token-wise embeddings. You sum over these embeddings. You will get one vector corresponding to sentence 1. You will get one vector corresponding to sentence 2. To find out the cosine similarity between them, that is going to be the similarity between the two words, two sentences. Okay. Then vector extrema is another model, another way to kind of find out the similarity. What it does is the following: that you again pass the same sentence, the two sentences through BERT one by one. You will get those token-wise vectors, right? This time you do one thing, that for each of the dimension, for these two vectors, you pick the value which is higher. Right. So earlier you were doing what? You're doing what? Averaging. This time what you are doing? Just pick that value which is the highest instead of averaging. Right. To create the final vector. And then you again find out the cosine similarity between these two final vectors. Okay. Why it works? What is the intuition? So it just does well in the downstream task. That's the kind of empirical intuition behind it. But yes, this again was a kind of a popular way to combine vectors of multiple tokens that are there in a sentence, right? You pick that dimension, or for a dimension you pick that value which is the highest among all. Yes. So suppose like you have a 3 token sentence, right? So you are going to get 3 different vectors. Now you have to create an aggregated final vector. So you pick the first dimension, you take that value from these 3 vectors, which is the highest, and you just project that to the final vector. Right? That's how it is. That's how it has been proposed. Okay. Again, these MENT and YISI. So these are, I think, from the same group. And they use some sort of weighted averaging also, right? So again, this weighted averaging is they trained some model to get these weights, and then you kind of combine the weights based on these trained weights. Okay, again, this is more the neural side, where you are getting some embeddings at the top, but you don't combine them in a simple weighted average, or you don't pick the max based on the maxima. You have some weights corresponding to each of the token, and these weights are the trainable parameters of the model. Okay, and that's how these two models are also proposed. Okay, what has become more popular is this second idea. That's this second this BERT score, right? So in the first 4, I think all of them used cosine similarity as a metric to find out the similarity between the two vectors. This one is kind of a different similarity metric itself, right? This is called BERT score. So what the idea is the following: that suppose you have a reference sentence, the weather is cold today, and you have the candidate sentence, and you're calling that as X prime, it is freezing today. You pass again the 2 sentences to maybe BERT, right? Now BERT will generate what? Same thing, token-wise embeddings. That's what you are seeing here. These are the token-wise embeddings. So for this has how many words? So suppose this has 5 tokens, right? The weather is cold today, and it has 4. So This is going to have 5 embeddings and this is going to have 4 embeddings, right? Then you find out cosine similarity between the pairwise embeddings. Right, then you find out the cosine similarity between the pairwise embeddings. So one from the candidate, one from the reference, you find out the cosine similarity. Once you'll do the cosine similarity, can you get this kind of a matrix? Right, so this is what? This is the similarity of the word the with all the words that are present in the candidate. Right, this is the similarity of the word whether with all the words that are there in the candidate, and so on. Okay, now what you're going to do is, you do this first thing, and then you also calculate the IDF. How many of you know TF IDF? So what is IDF? Inverse document frequency. How do you calculate that? What is the intuition behind IDF? Why do you need that? Inverse document frequency. Find out the no, but what is the actual, like, why do we need IDF? Like, what is the intuition behind IDF? Frequency in a given document or frequency in all the documents, or the presence in all the documents? Okay, okay. Then why not we just pick term frequency, TF, right? If you talk.
You're talking about a collection of documents. So how a specific a word of interest is contributing has an importance in terms of the collection of documents, like IDF, like its presence in multiple documents in combination with the term frequency and specific, so it can be in.
So what is the difference between, why do we multiply these two terms, TF and IDF? Not exactly correct. I will explain, but that's not the correct answer. Yeah, yeah. Yes. What is more important? Word rarity is more important. Okay, okay. So how do you define this importance? Right. Oh, yes, this is kind of more closer to the correct answer, right? So I'll just describe why this TF and idea was proposed, right? So whenever we talk about TF, so TF is most of the times with respect to a single article or single document, right? So if suppose we are talking about some Wikipedia article, let us consider maybe Wikipedia article about Narendra Modi. Okay, so the word Narendra Modi will appear many times in his own article, right? But the word Narendra Modi will not appear that many times in other articles. Okay, so what does this TF talks about? That this word Narendra Modi is an important word because it is appearing again and again in the same article, right? But it will not become important, or it does not convey information if Narendra Modi is appearing in all the documents across, right? That means that this word is kind of a frequently occurring word. It doesn't have any specific meaning to it. Maybe it is just used as some sort of a connective, right? To a word which gives a grammatical structure to some of the sentences. Okay, so that is where IDF is proposed. So IDF just says that if the word is rare, that means it is not the frequency, but if it is occurring in less number of documents, that means that word is rare and it carries more it carries more information. Okay, that's a simple idea behind idea, right? But whenever we talk about TF, so TF is specific to a given article. That's why we multiply TF with IDF. Okay, so in this case, what is IDF? Because see, if you see this again, I need to, I think I need to just maximize it. So I'll just show you. So this is fine. This matrix, this Matrix construction is fine, right? We also have calculated some IDF weights. What are these IDF weights? So these IDF weights are created or calculated from the reference summaries. Okay, so there can be multiple references for a given example, right? So, and each reference summary can be called as one document. So there can be, suppose, five such documents for each of the input, for each of the training instance. Okay, so you are calculating this IDF over 5 documents, right? So if the word is occurring in all the documents, all the 5 documents, that means that might not be very words, that might not be very important word to look for, right? But if the word is occurring in maybe 1 out of 5, that word might be, we must kind of put focus on that word. Yes. Yeah, so this idea, the way this IDF is calculated in this BERT score computation is based on the presence of, so for example, this one, right? This the, how many times or in how many documents the word "the" is present. Inverse of that. What are the documents? The documents are the reference summaries for each instance. So for example, suppose you are given some candidate sentence, and for that candidate sentence, you have 5 reference summaries, right? So those are the 5 reference documents. IDF will be calculated on that. So BERT score is calculated for a pair of sentence. I have not yet told you how this BERT score finally is calculated. What I have told is this construction of this matrix, right? So I'll just reiterate once again. See, you started with this reference sentence, right? And then this candidate sentence. Candidate is generated from the model, reference is from the human. Okay, you pass this reference and the candidate from the same BERT model. You got these embeddings, right? You have find out the cosine, pairwise cosine similarity. You got this matrix, right? Along with this matrix, you also create this vector. This vector is the inverse of the document frequency, 1 upon df, right? Again, it is properly normalized, but 1 upon df. Okay, so if this word "the" is present in all the reference summaries, and when I say reference summaries, so this is just one reference summary, there might be multiple reference summaries, right? Then this is not very good word, it doesn't carry any semantic information. Okay, so we calculate this IDF scores for each of the word that is there in the reference summary, the current reference summary, and this is how we calculate the BERT score. So what we do is, for each word that is there in your current reference summary, you pick the highest similarity and then you multiply this with the IDF value. Yes. That will be this. So this is mostly to kind of take care this the stop words. That is how I think they proposed here. Yes. Yeah. Because stop words are going to occur in almost all the reference summaries. And so this is one such reason that I can give. The other reason is that we want to create diverse summaries. Yeah, they will be present. Yes. So their IDF score probably will be lesser, will be kind of less. But their cosine similarity will be higher with the words that probably you'll find it from in your this thing. Yeah. Yes, yes. This is for one such sentence. So this is for one pair of reference and the generated. Right. So you might generate so you have generated one sentence, right? Now you have multiple references. You are going to compute this BERT score with multiple reference summaries. Okay, so this is just for one, but IDF score will be calculated across multiple. Okay, so this is another way to calculate similarities. Yes. I think they have not considered any sort of thresholding here. Right. And again, if you talk about the summaries, the reference summary, they usually they don't go beyond 5. Beyond 5. Oh, so then they will just truncate. They're going to truncate it. There are papers around that where they showcase that models are sometimes biased towards longer sequences, sometimes they are biased towards smaller sequences. I'm not very sure about how it works in case of BERT score, but I'll show you one example later which showcases that if your model is producing longer summaries, longer generations, then the model will assign a higher score to that to those set of summaries. Right, so that is there, yes. Right. I'm not sure of BERT score. Maybe we need to see the papers which have come after BERT score and show that these are the issues with this particular metric. But again, BERT score has been very popular, where people don't want to use the cosine similarity between the embeddings, but they want to kind of use a different metric. Okay, so this is another, so this is a kind of what we have seen till now is two different types of models. So one is where like you just have a BERT kind of a model, you pass the sentences, generate the embeddings, find out the cosine similarities, right? BERT score is a different kind of a like a development on this, right? Where again you generated the summaries, you find out the cosine similarities, you generated that metric, you also calculated IDF scores, combine those IDF score with the maximum similarity, and you calculated this BERT score, right? Then there are models like this one, BlueRT. Okay, what they have done is this model is kind of similar to the way the BERT model was proposed, right? So in BERT also you have this next sentence prediction as one of the objective function, right? So they also did something like that. Their objective is whether the two sentences are similar or there are two sentences. They will do some minor perturbations in the two sentences, and then the model has to predict whether these are the two exact sentences or not, right? So what kind of perturbations you can do? Maybe you can paraphrase one sentence. You can delete some of the words in one of the sentence. You can mask some of the sentences, some of the words in one of the sentence, and so on and so forth. And then the model has to decide whether these two sentences are actually the same or not, or similar or not. Right. So at the test time, what you have to do, you just have to pass the two sentences and you have to see the label that you get from where? Where do you get the final label? Which token you see? CLS. Right. So you just add a feed forward layer on top of CLS. You just train your model and see what is the label associated with the CLS. Right. And based on that, so again, this BlueRT is not kind of a cosine based anywhere cosine is used. It is a new kind of an architecture. Right, where the sentences are handcrafted with a lot of perturbations. Again, I told you 3 different types of perturbations, but a lot of different types of perturbations, and you train your model to learn those perturbations. Okay, so even if two sentences have no lexical similarity, but they have semantic similarity, the model will train itself to learn that kind of similarity. Yeah. No. So suppose you have a sentence, one sentence, right? Then you are perturbed that sentence, and that is your next sentence. Now the task is, the objective function is whether these two sentences are same or not. Okay, so you have to train your model like that. In case of BERT, what is your task? Objective. You have one sentence, you have another sentence, whether the second sentence is the continuation of the first sentence or not. Right. Here the objective function changes, whether these two are same or not. Right. Now you can perturb in different ways. One way could be that you keep the original sentence as it is, you delete some of the words which are there in the original sentence. Right. And then that is one perturbation. Another possibility could be you just rephrase the original sentence, create one more sentence. right? Another possibility is you just mask some of the words in the first sentence, create the third type of perturbation. One more is where you can change the ordering of the words, ordering of the tokens which are there in the original sentence, and create this fourth type of perturbation. So they proposed a set of perturbations, and each perturbation can create multiple such sentences, kind of a perturbed sentence from the original one, right? And then you train the model like that. Yes, yes, yes. They maintain that. Yes, that's how they have created their training data set. So lexical similarity means maybe the perturbations will the way you are going to do perturbations, they will have lesser lexical similarity. When I say lexical similarity, maybe the number of words which are same is less, but still they are semantically similar. That is how they prepare their data set. Right. So you can use chat, you can give a sentence to a chat GPT and maybe you can ask to paraphrase it. Okay, that could be one such instance with which your model can be trained with. BlueRT is kind of an architecture. It's a simple adoption of the BERT architecture. So BlueRT is not a kind of a it's not a it's not a cannot you cannot use it as a encoder model, right? Even though it is a simple classification. It's kind of a using BERT for doing some sort of classification. And the classification task is whether the two sentences are semantically similar or not. Right? You have changed the objective function. That's all. Nothing special. Yes. BlueRT you can just adopt BERT. Yes. 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 That is true. That is true with almost all the data sets, right? All kind of models, right? So models will do very well on the data sets on which they have been trained on. Right. So again, that is what we see. We have seen the same thing in our model also. So in our case, the perplexity for on our data set was much lower than we got on some additional data set, on some other data set, right? And the model which was trained on that data set, it has given very poor perplexity on our data set. That is there. That is going to happen. Yes. Yes, 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 yes. So these are at least the one that we talked about. The last three, we are not talking about any syntactical similarities. We are mostly talking about semantic similarities. Uh, just just 1 second. Where? Mm-hmm. So grammatical, no, but this model was trained for semantic similarity. That is how this model has been trained. At least in the paper, they didn't talk about any sort of syntactic similarity metric, right? They only talked about semantic similarity based metric, and they compared also with models which were proposed for semantic similarity, right? Possibly they have done some sort of qualitative analysis where they have said that the generations on, again, they don't do any generations. Again, this is more on the data set that they have prepared. So those were grammatically correct on which the model has been trained. I think they have not done that. So that is what not they have done. This is more on the similarity only, whether the two sentences are similar or not. That's all. Yeah, yeah. That is what I remember. Maybe you can visit and you can see what they have exactly done. Okay. So then there was one more experiment which was done where which was done on this extreme summarization data set. Again, this is a very popular data set. It is called extreme summarization. And what it has been shown on that data set is the following, that not all summaries are very faithful, right? So this data set was created where maybe you have some passage and you want to summarize that. And this was done by humans, right? Yes. Full screen mode. Okay. Yeah. Okay, so not all summaries were faithful to the same extent. Some were less faithful, some were more faithful. So the model was trained, different models were trained on different faithfulness scores, right? But it was seen that even if you train your models on this kind of a setup, your performance is not going to improve, right? So if your reference summaries are not very faithful, then whatever you do, your model summaries are not going to be very good, or you're not going to improve on that, right? What they have done is that they later create another version of the same this same X some data set through some freelancer writer summaries, which were very faithful, right? And then they trained multiple models on these faithful summaries. So what they have shown is, as you kind of come up with summaries with higher faithful values, the model will also start performing, right? So that is what this says, that if your actual references are not very faithful, whatever you do, the model summaries will be kind of uncorrelated with the faithfulness score, right? Whereas if your expert references, they are good, then your model performance will also become correlated. So that's what they said, that the reference based measures are only good as their references. If your reference summaries itself are not very good, then the generations that you're going to get at the end are also not going to be. That is kind of intuitive, but that is what they did. Again, I think they employed some more people to do that. Again, the this faithfulness score is based on some manual evaluations. Okay, so whatever we have seen is the following, or the crux of what we have seen in the last few slides is the following, that it takes a lot of effort in creating these reference summaries, references, right? And again, there is no guarantee that whatever we are getting is the best, right? We need to do a lot of other manual evaluations on whatever has been created by references or by experts. Okay, so this is where maybe a new set of evaluation schemes were proposed, which are called reference free evaluation, right? Where you do not create any kind of reference translations or reference summaries, but you use some existing models to evaluate the other models. Okay, and alpaca eval, empty bench are some such examples, right? So what you do here is the following, that suppose you have built maybe one language model, right? You want to evaluate that language model. So what you do is you employ GPT-4. So whatever generations are coming from your language model, you pass it to the GPT-4, and then GPT-4 will evaluate your language model, how good it is. Okay, so that is called completely reference-free evaluation because there is no human in the loop. Okay, we'll see some examples next. Okay, so and the final one is like the human evaluation. So human automatic metrics fall short of matching human decisions. Human evaluation is more important part of evaluation of text generation. Gold standard is in developing automatic metrics. New automatic metrics must correlate with the human evaluation. I'll talk about that. Okay. So what the idea is the following, there is one possibility that we can just employ humans, right? It's okay, they are costly, but let us employ humans. That's all fine, right? So money we can afford, but let us just employ humans. But still there are some issues. The problem is whatever human evaluations you are going to do on the generation tasks, these are not reproducible. Right. So I will employ my set of experts, right? And then probably you will employ your set of experts. My set of experts might have a different expertise level than your set of expertise, right? Then whatever numbers you have reproduced, that my model is this much good, right? And my evaluators will say, no, no, this is not that good, right? Even same evaluators evaluate after 1 month, they might also differ in their decisions. Okay, so it is not just about money that you are going to invest. It is also about the reproducibility. You might not be able to reproduce the same annotations that humans have done on a period of kind of maybe just 1 month or a few weeks. Okay, so there are a lot of things why a lot of properties with why humans are employed for evaluations, right? So one could be fluency. How fluent is the text, right? Machines might not be able to capture this property very well, right? So this is where humans can be employed. So fluency, coherence, consistency, factuality, correctness, common sense, style, formality, grammaticality, and redundancy. These are some properties where humans can be employed, and you give them text, they will assign some scores. Okay, again, this is very difficult to do in the real scenarios. Okay, just read this note. Don't compare human evaluation scores across differently conducted studies, right? So the idea is very simple. Suppose I am evaluating GPT-4 and you are also evaluating GPT-4. You have employed 4 people. I also employed 4 people, right? You got some other scores for each of the metric. I got different scores for each of the metric. Again, even though they look like similar, but you cannot compare. That is the problem with the human evaluations. Okay, and these are those set of such challenges with the human evaluation. It is slow, it is expensive, inter-annotator disagreement. The different people have different expertise levels, so there might be very high inter-annotator disagreement, and then intra-annotator disagreement across time. So same person might generate something else after 1 week because it has acquired some knowledge. Okay, that is also, that can happen. People have shown that it actually happens, right? Results are not reproducible, precision not recall, and the biases, shortcuts if incentives not aligned, right? So for example, I employed people, I'm paying them $1 per hour, and you employed people, you are paying them $10 per hour. Right, which annotations are going to be better? Yours. Okay, so there is a lot of discussion in NLP where like what should be the incentive that should be given to annotators for good quality data sets, right? Even very recently, like I think last year only, they introduced one more section while you submit a paper that have you given any incentive to people you have employed them as annotators, and how much was that? Okay, so if you have not given any sort of incentive, then probably your annotations are not of very good quality. It has been proved in literature, right? So again, there's no threshold that you should pay them at least 10 hours, $10 per hour, but again, you should pay them some good amount to get good generations or good annotations. Okay, so these all factors matter. And this is where like human evaluation, even though it is good, but it is kind of difficult to do and to reproduce, even if like you have kind of recruited good set of people. Okay, the last line is from one of the paper which did some sort of human evaluation and the quality of human evaluation study. Just read this sentence once, and you can understand the problem. So only 5% of the human evaluations are reproducible. They did experiment on like a very large kind of set of studies which have done human evaluations. Just 5%. Right. So what it says is, I hope it is understandable. What they say is just 5% of the human evaluations are repeatable or reproducible, in the sense that there are no prohibitive barriers to repetition, that we can do the experiment Again, that is at least possible. The second is the sufficient information about experimental design is publicly available for rerunning them, right? You are, suppose you want to reproduce the results that were present in a paper, then at least all the information is available to do that same experiment again, right? If all this is possible, then just 5% papers are reproducible, right? If, and again, they contacted a set of authors also. So if authors reply back, okay, I'll help you in reproducing the results, in that case, it just increases from 5 to 20%. Okay, so that's the best scenario. In the best scenario, you are not going to get better than 20% reproducibility on the human evaluations. Okay, so these are the problems. I told you the benefits, like this, like the kind of things that humans can evaluate, machines cannot do. But then there are a lot of challenges also. Okay. Again, these are some descriptive issues. So suppose you have recruited some people, right? And these people are going to do some annotation for you. The problem can also come up the way you are describing the task to them, right? So how you are going to describe the task? Maybe I recruited 5 people, not have the same expertise in English, and I'm explaining them in English the task, right? They don't understand what exactly I said, right? So, and how to show the task to the humans, what metrics to use, selecting the annotators, monitoring the annotators, time, accuracy, and money. Money is not added here, but that is important, right? All this matters. While you pick annotators, you explain the task to the annotators, and then you finally get the results, right? So there are a lot of studies which also talks about that whenever you are recruiting some people for this kind of annotation task, you repeatedly visit them, maybe after one day, after a few hours, whether they are doing good or not, right? But again, that is not easy, right? If suppose you have 250 annotators, it's not easy to kind of visit each of the annotator and see if they are doing good or not, right? So that is difficult. Okay, so now we will talk about kind of a lot of benchmarks, lot of portals, lot of frameworks, libraries, where you can do this reference-free evaluation. No reference, no humans are there, right? But still you can evaluate the generations, right? So maybe this is about which two models? Maybe GPT versus Mistral, which is better? Okay, so the idea would be that how do we evaluate something like ChatGPT without employing any human, right? So many different use cases, so it is hard to evaluate because see, ChatGPT is not just for summarization. ChatGPT you can do translation also. ChatGPT you can do reasoning also, right? So then for each task, if you are going to employ humans, you require a lot of humans which are expert in different tasks, right? So that is difficult. The responses are also long form text. The generations from the chat GPT are going to be very long, or Bard, Gemini, all these are very long, right? Then it is difficult to keep annotated because they have to read this entire text and then they have to decide. That is again an issue with the human annotations. Okay. So this is a table, very nice table. This table was present in Instruct GPT, right? What it says is the kind of prompts people were giving to the GPT model. Okay, at that time. So they made GPT-2, I guess, open at that time, right? I think this is GPT-3, Instruct GPT. Okay, they created an instruction tuned version of that. They made the portal open where people can submit their jobs, submit their queries. And among the submitted queries, 45% queries were just about generation, some random task. And maybe some question answering. So some open question answering for 12.4, brainstorming was 11.2, chat was 8.4, rewriting was 6.6, summarization 4.2, and so on and so forth. Generation is some random. Again, all these are generations, but generation is kind of some random generation that they wanted to do from the Instruct GPT. Why this table is important? The only thing why this is important is the following, that the responses in the case of generations were very long, right? So at least half of the prompts that are going to be passed to the model will generate responses which are going to be very long, and keeping humans in loop is going to be very difficult to evaluate those. Okay, so we need machines, we need some other models to evaluate those, right? And this is where we'll talk about, okay, I have 5 minutes, so I'll just talk about this chatbot arena. How many of you have seen this chatbot arena website? Okay, some of you have seen. Maybe we'll just quickly revisit it and then we'll stop here. So whenever you open the chatbot arena website, you will get this disclaimer. Again, this disclaimer is kind of very interesting, and we should just read it once. Oh, so this is somehow not maximizing. Okay, so this says the service is a research preview. It only provides limited safety measures and may generate offensive content. It might not be used for any illegal, harmful, violent, racist, and sexual purposes. Please do not upload any private information. And then it collects the dialogue data. So the data is going to be collected. If I click OK, generates, it kind of opens this particular portal. What it is there that it is going to give you some, it is by default, you will be presented with two chatbots, right? Two different models. What you have to do is you will pass a prompt and the chatbot arena platform will generate the responses from two different models for the same prompt. You have to say which response is better, right? So whatever you say, so maybe whatever you say, so you can simply say right. So I'll just pass this as one of the prompt. Right. And then there are two different models. You don't know which model is which one. Right. So one could be GPT-4, one could be Llama also. Right. So this is the thing that this is the output that I got from two different models. What you have to do is the following. You have to just label the output, label the response, right? Which one is better as per you, as a human to you, right? A is better for the prompt that you have entered, B is better, this is a tie, or both are bad. Okay, I don't know which one is generated from which model. Okay, I can just say maybe A is better. Okay, now it showed like what are the models from which these two generations were happening. Okay, so this is how this website is collecting the data. Okay, so it is kind of an open platform. You visit this website, pass some prompts, and then you rate the models based on this, right? If the model identity is revealed in any of the response, then your label is not considered for those scenarios. Sometimes you can simply write a prompt that, hi, can you tell me who are you, right? In that case, the models are going to generate, I'm Llama and I'm kind of GPT or this and that, right? In that case, and if you say that, no, I will favor GPT for this, in that case, the response will not be considered. Okay, so response will only be considered in the case where the model didn't reveal its identity, it kept the response as anonymous. Okay, so they have collected huge amount of data. So I think this is almost this much, almost 1 million pairs where they know which response is better than which one, right? Again, this data is available, so you can use that data for research and training. Yes. Huh? How they? So now you have just randomly selected. I have randomly selected. The noise is always there. The noise is always there. There is a human in loop, but again, not at the real time. It's a near real time. There will be some human. There is a bias. Yes, there is a bias. There is a bias. There is other set of biases also. I'll not describe, but yes, it's going to be right. And based on this, what is going to happen is, see, so at the end, these were two different models, right? You rated one model better than the other one. So what they have done is they have created a chat leaderboard based on user feedback. So at the top, you can see GPT-4o, right? Cloud 3.5, Gemini 1.5, GPT-4, Gemini, GPT, and so on and so forth. This is based on user feedback. People who visit this website give their feedback, and based on that, they do it, right? Again, they do sort of filtering the way you do filtering on the IMDb reviews also. Okay, so they do sort of cleaning. Okay, but if you see here, again, I think this was shown before, where all the top ones are all proprietary. Till what point? Till 12. Again, this is, yeah, again, the number is much higher there. So all the top ones are proprietary models. Fine. So this is kind of a pairwise comparisons. Here you can pick two models based on your choice, right? So you can pick, no, I want to compare GPT-4 with Gemini. So you can just pick those two models and then you can generate the prompt, generate the response from the prompt, and you can compare. That is also possible. Okay, so that is also possible here. Then you want to do direct chatting, pick some model, chat with that, right? And that this is the kind of leaderboard. Okay, this is very popular model. Right. A lot of models which we are going to see, a lot of leaderboards which we are going to see next, they show that their automatic evaluation is highly correlated with the user responses that we have got in chat arena. Because these are human generated pairwise preferences. Right. So this is used in a lot of building a lot of other models. We'll see that later. Okay, that's all for today. Thank you.